Okay, so lecture notes for April 3rd, 2025. Uh, this is about rational functions. And what's a rational function? It's one polynomial divided by another polynomial. And so we want to figure out what the graphs of these things look like. There are three cases that we'll look at. The first is that the numerator, or the top function, has a higher degree than the lower one. Bottom. Two top and bottom have the same degree. And the third case is that the bottom has higher degree than the top. So we'll start with case one. We'll do sort of a typical example of how this sort of thing works. So we'll start with a function. Our rational function is f of x equals x plus 3 over x minus 5 quantities, times x minus 5 quantities squared over x minus 1. So three factors, except one of them is actually down in the denominator. So this is a degree 3 polynomial, right? 2 degrees there, 1 there. This is degree 1 because just one factor to the first power. So what does the graph of this look like? Well, remember that the first thing we want to check actually is what's the domain of this? And it's all x so that the bottom does not equal 0 because we're not allowed to divide by 0. So all x except solutions to the equation x minus 1 equals 0. So x is not allowed to be minus 1 because we have, not allowed to be plus 1 because we set x equal to plus 1, we get a 0 in the bottom, and that's a problem. So that's a thing that we haven't had to deal with polynomials. A lot of this, though, is pretty typical from polynomials. How do we actually graph this? Find the end behavior. And the end behavior is sort of like we did with polynomials. It's roughly the highest power in the top, the leading term in the top, over the leading term in the bottom. And in this case, that's going to be x squared. Oh, sorry, x cubed, right? Because we've got 1x here and 2x's there over x. So that's x squared. That's positive coefficient, because the coefficient is plus 1. And it is a even power. So that gives us our end behavior, and we like that. So our graph, we'll start our graph over here on the side and do some calculations to its left, is going to end up looking like this. It'll look like its end behavior will be like an x squared graph. So if we go back up here and look at this, we can look for x-intercepts. Again, that's where f of x equals 0. F of x here, our function, is x plus 3 times x minus 5 squared. over x minus 1. And we want to solve this for x. And what's nice about this is we can just cancel out the x minus 1s, right? We'll just multiply both sides by x minus 1. This cancels that. And 0 times anything is just 0. So we only need to worry about the top to find out about x-intercepts. Try and spell that a little bit clearer. And we know what we've got then. X equals minus 3, the multiplicity of 1, right? And that's an odd power, which means the function changes sign. And we have x equals 5 with multiplicity 2, which is an even power, which means that the function does not change sign. Oops. Actually, we want to use a slightly different language for that. It means same sign. So over here somewhere, there's an x-axis minus 3. And over here, there's a 5. And then the other question is, what happens to this function? Don't know why I did that. What happens to this function at the place where it's not defined? What does the graph look like there? And the answer is we get something called a vertical asymptote, which some of you may have seen, but we'll walk through what that means. So vertical asymptote means that we have the following behavior. Our function is x plus 3 over x minus 5 times x minus 5 squared over x minus 1. So near x equals 1, the top is near 4 times minus 4 quantity squared. So if we just plug in 1 into the top, we get 4. And 1 minus 5 is minus 4. You square that, you get 16. So this is 64. The bottom is near 0. And that's what's going to create our issues. So suppose we have f of x. We take x equal to 1.1. So that's pretty near x equals 1. What is f of x equal to? Well, it's going to be 4.1, because if we set x equal to 1.1, add 3 to that, we get 4.1, times 1.1 minus 5, which is minus 3.9 squared. And this is going to be pretty close to 64, because this is pretty close to 4, and this is also pretty close to minus 4. But the denominator is going to be 1.1 minus 1. And so when we subtract that, we get 0.1. What happens when you divide by 0.1? Well, keep in mind what 0.1 is. 0.1 is 1/10. And when we're dividing by a fraction, you multiply by the reciprocal. So this becomes 10 times 4.1 times minus 3.9 squared. And that's about 640. Because this part here is about 64. And then we're multiplying by the 10 that came from the denominator. So that's 640. If we have x equals 1.01, f of x is going to be 4.01 times minus 3.99 squared over 1.01 minus 1. Go through the same steps. You get, going over here, so there's some more space, 4.01 times minus 3.99 squared. That's really close to 64 now. 1.01 minus 1 is 0.01, but 0.01 is 1 over 100. So this becomes about 100 times 64, which is equal to 6,400. So as we get closer and closer to 1, right, 1.1, 1.01, the y values that are getting out are getting bigger and bigger and bigger. So what actually happens there is as x goes to 1, from the right, y goes to infinity. And you can do the same kind of things as x goes to 1 from the left. Y will go to minus infinity, because instead of having positive numbers on the bottom, if you had 0.99, you'd end up with negative numbers on the bottom. Okay, and so this tells me that I've got a vertical asymptote. That's what a vertical asymptote is. You're going off to plus or minus infinity. So when we go back to our graph, how do we handle that on our graph? We put in at x equals 1, a dotted line, a dotted vertical line. On my open math, I'll make it a solid line usually. So x equals 1, and that's our vertical asymptote. So we want to sketch the graph. What are the rules for sketching the graph? First rule, can only cross x-axis. We even touch the x-axis at x-intercepts. Cannot cross vertical asymptotes. You go to plus or minus infinity instead. Basic rule of thumb, even power, same sign, odd power, opposite sign. And the last thing is start with the end behavior. If possible. So rules for sketching rational functions. And we'll add a couple of other rules later. So what do we do here? When we're looking at this, we have to start up here with our end behavior. We have an x-intercept here, a vertical asymptote here, and another x-intercept here. So we can't cross the x-axis except at this point, and at that point, we can't touch this thing. So how do we deal with this? We start here, come down to this x-axis, to this x-intercept. That's minus 3. Its multiplicity is 1, which is an odd power, which means you change sign there, which means you go through it. We're positive on one side, y values above the x-axis, and our y values are negative on the other side. So what we're talking about here when we're talking about changing signs is your y values. Do your y values change sign? So now we go over here. We've successfully dealt with that. We come over to our vertical asymptote. Now, we're not allowed to touch that, but we're also not allowed to go through the x-intercept, right? The x-axis. So when we get to the vertical asymptote, we have a choice. We can either go up to positive infinity or down to negative infinity. But here we can't go to up because you can't cross the x-axis. There's no x-intercept, right? So there's no x-intercept in here. And so when we're getting to the vertical asymptote, we can't go up to positive infinity. We have to go down to negative infinity. Okay, so at a vertical asymptote, we go down. The vertical asymptote, right, as x goes to 1 from the left, y goes to minus infinity. We got that. And from the right, we go to positive infinity. Note that this was x minus 1 to the first was the factor in the denominator. Odd power. Y values have opposite signs on either side of the vertical asymptote. So on the left, when we went down to minus infinity, that means on the right, our vertical asymptote goes up to plus infinity. And so then when we come down from here, we get to this x-intercept, but that's an even power, so we have the same sign on both sides, and we go back up. So we're plus on this side, plus on this side, plus on this side. So we have an odd power for the x plus 3. So we switched sides. We went through the x-axis. We had an odd power on the x minus 1. So we have a minus sign on one side and positive on the other side. Changed sign. The x minus 5 had a squared. And so that means we don't change sign. That means we stay on the same side of the x-axis, positive y values on both sides. And there's our graph. We can let's see, graph this on GeoGebra. And this is what our graph looks like. If you just graph it, it looks a little odd because we're not quite sure what's going on. But we can ask it to plot our various points. So one point was minus 3, comma f of minus 3. And that is our x-intercept that we went through. And then 5, comma f of 5. Oops. F of 5. Right? That gives us other x-intercept. We can plot a vertical asymptote just by plotting a vertical line, x equals 1. And so if we look at the graph, right, it looks kind of like what we had. The numbers are much bigger, or y values are getting really big here as we go out. And so there's our vertical asymptote, but you can see we go up to infinity on one side, down to minus infinity on the other side. And so we can actually look at this a little bit. The numbers we had were 1.1 and f of 1.1, right? And so that gave us 1.1, 624. So if we get close to 1, x equals 1, if we're at 1.1, our y values are way, way up. So where are y values? 623. So you have to zoom way up to get to f of 1.1. The y value is really big. If we get even closer, 1.01, comma f of 1.01. Right now you're out at 6,400, and you have to scroll out a lot to be able to see that because you've gone way up there. And you notice that we are also even, right? As we go up here, we're going up to plus infinity on both sides. So our graph is correct in that our sketch got us the right characteristics of it. We know where the graph is positive, where the graph is negative, and where it goes to infinity. We didn't get the exact numbers right because we didn't actually plug that in, and we're actually not that interested in what those numbers are. So let's see, go to back to our lecture notes. So more or less the right picture. It should be much steeper, but that's okay. So what about case 2? So here we have the same power on the top and bottom. And we will look at this function. And I'm going to throw in some factors that we're going to be able to cancel out just to show you what happens in that case. Great. So again, what's the domain? The domain is all x's except those that make the denominator 0. So domain is we're not allowed to use x equals to 2 because that makes this term 0. We're not allowed to use x equals to 0 because that makes this term 0. And we're not allowed to make x equal to 7 because that would make that term 0. Okay, we can simplify this and we'll call that a different function g of x. I can cancel out this -8 and this 2. That would give me -4. These get canceled out. And I'm left with an x plus 1 cubed times an x plus 3 over x squared, x minus 7 squared. What's the difference between this one and that one? Notice that the domain here is x is not equal to 0, x is not equal to 7. They're not exactly the same thing because this function, you're not allowed to use 2 in it. But it canceled out. So what does that mean when we come to the graph? And so we'll see what happens there. So for f of x, or g of x, they're pretty much the same. F of x is, we'll put dots there. We want to know the end behavior. That's the first thing we want to look for. And so we take the ratio of the leading term at the top, which is -8, and I've got 2, 5, 6 x's in the top. And in the bottom, I have 2, this should be y equals roughly 2, and I've got 2, 4, 6 x's in the bottom. Why this little squiggle? It means that I'm not getting y equal to -4, but y is approximately equal to -4 for very large x. And that could be either positive or negative, right? So when we're way out to the right or the left, the graph should have y coordinates that are about the -4. So that's our end behavior. Great. X-intercepts, easy to find. X equals -1 is definitely an x-intercept with multiplicity 3, which is odd. So our y values change sign. We go through the x-axis, and x equals -3 with multiplicity 1, which is odd. The y values change sign. X equals 2 we'll be a little bit careful about because That's in our list of forbidden points. Vertical asymptotes, we know there's definitely going to be two of them because we see those from the denominator. X equals 0. That's this one would be a vertical asymptote. And that's got multiplicity 2, which is even. Y values will not change sign. And x equals to 7, which has multiplicity 2, which is even, so y values don't change sign. So the denominators give you your vertical asymptotes. The numerator gives you your x-intercepts. The question is, what happens when we have something that cancels out? And that is actually what's called a hole. It doesn't produce a vertical asymptote or an x-intercept. And we'll see exactly what that means in a moment. So from this, what does our graph look like? Well, our end behavior is y equals -4. That's a nice horizontal line. So our end behavior is like that, y equals -4. This is a line, and it'll go all the way across, of course, but we're only worried about it for x really big. So the end behavior is way out here and way out here. That's where the graph is going to be. So the graph is y values about -4 for very large x. X equals -1 and -3 are our two, then x plus 3, yep, are our two x-intercepts, -3 and -1. And we change sign. That means we go through it. At x equals 0, we have a vertical asymptote. That's even. X equals -1 is my x-intercept here. That's odd. X equals -3 is my x-intercept there, and it's got odd multiplicity because it's an odd power. X equals 7, and that's got a multiplicity of 2 because it's x minus 7 squared. That'll be out here somewhere. That's our other vertical asymptote. Great. So following our rules, we'll go from left to right, start with the end behavior, go through, deal with this x-intercept, vertical asymptote, back to the end behavior. So we start here. We're below the x-axis. We go up to our first x-intercept. It's an odd one, so my y values change sign. That means I go through it. I'm minus on one side, y values are plus on the other side. Next feature I come to is the next x-intercept. That's here. It's also odd, so we're going to be positive on one side and negative on the other. This is a vertical asymptote at x equals 0. Again, I can't go up because there's no x-intercept between -1 and 0 for my graph to go up through. So I can't go up this way, but I can go down to -infinity, right? With a minus sign. Down to y values go down to -infinity. This is an even vertical asymptote. That means we have the same sign on both sides. So we have to have negative y values on the other side. So we go down to -infinity on the right side of the asymptote as well. And then we come up here. This dotted line is the horizontal asymptote, y equals -4. it doesn't matter if we're in this area. It doesn't, like the horizontal asymptote isn't important. The horizontal asymptote is only important for end behavior. So we go up a little bit. We come over to this vertical asymptote. Again, we can't go up to plus infinity because that means we'd have to go through the x-intercept and the x-axis, and there's no x-intercept there. So we go down to minus infinity. Again, this is even. So if I'm negative on one side, I have to have the same sign on the other side. So I'll be negative there. We come down like that. And so we go up and draw in our end behavior. So there's our graph. Except for, what was it? X equals 2. And so in graphing this, it looks like, it goes right, it should go right past here, but it's not defined there. So we just put a open gap, an open hole. What's the Y value that we would see there? Well, once we cancel out the x minus 2's, we get this function. If we just plug x equals 2 into that, and that's going to be minus 4 times 2 plus 1 cubed, because that's the x plus 1 term, 2 plus 3 over 2 squared. That's our x squared in the bottom, and then minus 5 squared. So it's going to be minus 4 times 8 times 5 over 4 times minus 25. Plus 25, because the minus 5 squared, the minus sign goes away. So we cancel out a 4's out of the top. We cancel out a 5 out of the top and a 5 out of the bottom, and we're left with minus 8 over 5. So there'll be a hole there at x equals 2. And to figure out what the y value would be, you just plug it into the simplified equation. Okay. So let's see. Let's go back to GeoGebra. And we'll get rid of this function. Oh, and we don't need this either. And this is the function that we graphed. Okay. Our end behavior was the horizontal line y equals minus 4. And if you look at this graph, the red graph, for very large x, it's pretty much the same as y equals minus 4, right? It meets that graph. So the y coordinates of the red graph are pretty much close to 4, minus 4 from very large x and y. Now, if we go in here, right, we do see that we don't, well, we do see the two vertical asymptotes. One is at x equals 0, there's that blue one, and the other one was at x equals 7. And we should probably make that blue as well. Kind of a different blue, but that's okay. So there's our two vertical asymptotes. If you zoom out a little bit, you can see that they're going down there. And you can see that since they're even vertical asymptotes, we have the same sign on both sides. These y values are both negative there. And we come up a little bit. We had some intercepts. So one x-intercept was at minus 1. Oh, g of minus 1. And the other one was at minus 3. Right, so those are two x-intercepts. The graph is actually positive in between there, except it's very, very low. You can see it sort of being a little bit positive there. And so finally, um, what's g of 2? Well, g of x is this thing. It's got an x minus 2 in the bottom, even though there's something that cancels out. So technically, that's not defined at all. So h of x is the same function of g of x, but just everything simplified. And so you can see that g of x and h of x have the same graph. But we can plot of h of 2, and that's down there. So this is where our hole is. So technically, when we're graphing this, so we get rid of that. We want a little hole at that point because this function g of x is not defined there, but it behaves as if it was this h of x. So if things cancel out entirely, you get a hole instead of a vertical asymptote. And so there's our graph. This green line is our horizontal asymptote. The blue lines are the vertical asymptotes, two x-intercepts, and a hole. Okay, so that's that case. So let's go back to our notes. Um, okay, and then last thing is case 3. Higher power in the bottom. And the example we use is a function. Um, 2x minus 2, x plus 2 squared, x minus 3 squared, all over x squared, x plus 5 cubed, x minus 5 cubed. This one is already simplified, so we don't have to worry about that. So, end behavior. Oh, domain is first. X can't be 0, x can't be minus 5, x can't be positive 5, because that's where these three terms would be 0. These would all be vertical asymptotes because they don't cancel anything out. And they're all, well, x equals 0, vertical asymptote will be even. These two are odd. X-intercepts, oh no, now we do the end behavior. So ratio of top, highest power in the top, ratio of leading term in the top to leading term in the bottom. So we have a coefficient of 2 in the top, and then x, 2 more x's, 2 more x's, so that's 5 x's. And then we've got an x, and then 2 x's, and another 3 x's, and another 3 x's, so that's 8. So 2 over x cubed, what does that mean? If we make x a really, really big number and then cube it and then put in the denominator, right? 2 over a huge number is pretty much 0. So if we have a higher power in the denominator than in the bottom, our horizontal asymptote is going to be y equals 0. And that's going to pose a little bit of a problem because we won't be able to actually start our graph with the horizontal asymptote. And last, x-intercepts. And you can do these in various orders, finding the vertical asymptotes and the end behaviors and the x-intercepts. X equals 2, and that's odd because we have an odd power there. X equals -2, and that's even. And x equals 3, and that's odd. No, that's also even, right? So odd and even refer to the powers on those things. So that gives us our graph, or at least the important bits of the graph. So x-axis, y-axis, and behavior is just y equals 0, which is the x-axis, right? And then the x-intercepts, we want to have one at 2, x equals 2, which is odd. We have one at -2, which is even. We have one at x equals 3, which is even. And then we have vertical asymptotes that we looked up here, 0, -5, and 5. X equals -5, and as a vertical asymptote, that was odd. X equals 0, which is the x-axis, and that was the even. And then x equals 5, another vertical asymptote, and that one was odd. Now, where the question here now that we're faced is where to start. In the previous cases, we used the end behavior because the end behavior was away from the x-axis. We definitely started negative, or we definitely started positive. Here, we don't know because our end behavior is 0. So where do we start? Well, pick a point. Pick an x value that's not an x-intercept or a vertical asymptote and find its y value. And that will tell us where the function is at one point. So if we take this function up here and we say, okay, let's take x equals to 1. That's a pretty easy number. What's f of 1? If x is 1, then y is going to be 2 times 1 minus 2, 1 plus 2 squared, 1 minus 3 squared, over 1 squared, 1 plus 5 squared, cubed, 1 minus 5 cubed, which is going to be something, right? It'll be 2 times -1 times 3 squared, which is 9, times 1 minus 3 is minus 2 squared, which is 4, all over 1 squared, which is 1, so we don't need to deal with that. 6 cubed is 216, and I know that because I'm a mathematician. I wouldn't expect people to know that off the top of my head. 1 minus 5 is -4, and -4 cubed is -64. Right? And you multiply all that out and see what it is. In any case, it's some positive number because this minus sign and this minus sign will cancel out. So f of 1, if we go back to our graph and we look at x equals 1, we know f of 1 is up here somewhere. So this is our point that we can start from. And so if we start from here and go to the right, following the usual rules, first thing we come to is this x-intercept. It's odd, so we go through. The next thing we come to is this x-intercept, and it's even, so we touch it and go off. And then as we come away from this, we're trapped by the x-axis above and the vertical asymptote to our right. And since we have to go from left to right, that means we have to go all the way down. This is an odd one, so if I'm minus on one side, I have to be plus on the other, and then I come down. There's nothing else for me to do but to just join up with my end behavior. Going to the left, first thing I come across here is a vertical asymptote. Again, I can't go down through the x-axis, so I have to go up to plus infinity there. This one is even, so if I'm positive on one side, I'm positive on the other. Even means same sign. So that means I go up to infinity there. So keep coming down to my left. We come to this x-intercept. We have to cross this. No, we don't cross. It's even. So same sign. We touch it. And then we climb this x-intercept. This one is this vertical asymptote. Positive on one side. Since it's odd, that means we have to be opposite sign. So negative on that side, and then we climb back up to our end behavior. And so there's our graph. So now I put this. In this particular case, where to start, pick an x value, find its y value in this case. Otherwise, start with the end behavior. And so we can go to GeoGebra. We can delete that function. We don't need it. We can delete that function. We don't need it. We can delete these. And this is our last function. So notice that our horizontal asymptote, the graph gets very close to y equals 0 as we go out to the right and the left. Our vertical asymptotes are x equals 0. Blue is a bad choice for that. Let's make that red. X equals -5 and x equals 5. And we'll make those both red as well. So those are various asymptotes. We have a horizontal asymptote. That's the x-axis and 3 vertical asymptotes. We should have at 2 an x-intercept there. An x-intercept there, right? So we're getting zeros for a y value. And then finally, an x-intercept there. So there's our graph. And notice when we looked at our graph before, right, we should be negative between those two. Oop, I'm having some issues here. Okay. Can get back to my GeoGebra. Oh, there it is. Okay. So in between these two, you zoom in super close, it looks like it's just along the x-axis. But if we do, say, f of 2.95, wow, it gives you back 0 because it's just too hard to compute. It's too close. Huh. 2.5 comma f of 2.5. Wow, that gave me 0 as well. That's a little weird. Um, it's very small there. But we calculated f of 1. Oh, I know why it's giving me that. It's j. I want j of 1, not f of 1. There's no f anymore. J of 1. There we go. There's that point. And then what's 2.5 comma j of 2.5? And I don't know why I'm having commas instead of points. Point. What's that? Ah, so that's negative. So this is actually negative by a very little bit. So we went from positive on one side to negative on the other, even though the graph looks like it's just 0. So there's our graph. Um, and so that's graphing rational functions. And then we'll move on to exponentials and logarithms next.